Professor Clements with you as we talk about magnetic field due to current in a straight wire. If you're using the OpenStax College Physics book, this is in Chapter 22, we have a long straight wire that's vertical. It's in a room. A conventional current of 2 amps is directed toward the ceiling. We want to calculate the strength of the magnetic field 20 centimeters away from the wire, and we're only interested in the magnetic field created by the current in the wire. So I'm going to take a side view. We have our conventional current I, that's 2 amps, and it's headed up towards the ceiling in this particular room. Now, when we consider calculating magnetic field due to a particular geometry of wire, we're going to discuss 3 situations in my course. It would be a straight wire, a loop of wire, the magnetic field at the center, and the magnetic field inside a solenoid. I'm not going to go through Ampere's law and derive the formula for the magnetic field created by the wire, but we're just going to use the result of Ampere's law. The strength of the magnetic field is equal to mu naught, a constant, multiplied by the current, and then divide by 2 pi r. That's our formula to find the strength of the magnetic field some distance away from the wire. So we want to know 20 centimeters away from this wire, what's the strength of the magnetic field. And this distance is taken as a perpendicular distance away from the wire. So 20 centimeters away. Now, this is not a difficult process. We retrieve the value of our constant, mu naught, is 4 pi times 10 to the minus 7 in standard metric units. We were given the current, 2 amps. We have the constants 2 pi, and then r. R is the distance away from the wire. This formula would give us the strength of the magnetic field any place on a circle with a radius of 20 centimeters. So that's really why the R symbol is used. I do need to use meters when I do this calculation. So 4 pi times 10 to the minus 7, that's the constant for our magnetic formulas. And you should pause the video here and do this calculation in advance of seeing the answer. But pause now and see if you get my answer. And on my calculator, I came up with 2 times 10 to the minus 6 teslas. The steps I performed to get this answer was, I see here that I can cancel a 2 pi into 4 pi, leaving a 2. So 2 times 10 to the minus 7 on the numerator, times 2 divided by 0.2. You can almost do this in your head. The 2 divided by 0.2, that would be a factor of 10, and that takes us to 10 to the minus 6 instead of 10 to the minus 7. But that would be the magnetic field. Now, it's sort of an auxiliary question. What's the direction at the point of interest? What's the direction of the magnetic field? In this case, we use a right-hand rule for wires. In step 1, I put my thumb in the direction of the current. I now wrap my fingers around the wire on this circle, and what I find is that on the right side of the wire, my fingers are pointed into the paper. If I'd asked this question over on the left side of the wire and continue my fingers wrapping around behind the wire, as they come to this side, they would be pointed up out of the paper, and we draw that circle with a dot. So the magnetic field is into the paper here by virtue of using right-hand rule. Your thumb goes in the direction of current. The direction your finger points shows you the direction of the magnetic field. On the left side, that direction is out. On the right side, the magnetic field is directed into the paper. So keep practicing with that. Be sure you know the geometry of the wire that's creating the magnetic field.